Okay, section 4.1a, applications of the first derivative. So in this section, in the first half, we'll be talking about a couple of the applications of the first derivative. To begin, we're going to look at a graph. Let's suppose on the x-axis we have t, that stands for time in years. Then on the y-axis, let's say we're looking at the profit of a company in dollars. Let's suppose this company's profit starts somewhere here, and then it does this. So as you can see, as time increases, at first the profit is increasing, and then after a while it reaches a relatively high point, and then it starts to take a little dive and is decreasing. So how does this relate to the first derivative? If you were to pick a point somewhere on the graph here and looked at the tangent line at that point, you would notice that the slope of the tangent line was positive, which tells you that anywhere in this region until it attains this maximum point, if you pick any point here, the slope of the tangent line as you go from left to right is positive. Whereas if you go past this max, the way the direction of this graph is going, any tangent line here that you would draw would have a negative slope. In terms of derivative, what we have here is the statement that if f prime of x is positive, then f of x is increasing. If f prime of x is negative, or the tangent line slopes are negative, then the function f of x is decreasing. Now right up here at the point where you have a turning point, where the graph turns, or the turning point, notice that if you drew a tangent line, it would be horizontal. So if f prime of x is neither positive nor negative, if it is 0, then the function is constant. You'll notice that it's a flat line there. You could also, the way we describe where functions are increasing and decreasing is we use intervals on the x-axis. So if this number here was a, then you would notice that f is increasing here, and then f is decreasing. Okay, so you would write it in terms of this interval. When we do some examples, you'll see what I mean by that. You could also have a situation like this, where the function could first be increasing and then decreasing and then increasing again. Notice that it goes on forever, and this could also be going down in this direction forever. So let's say this point where it turns first as a, and let's say that is b, then you would say that from negative infinity to a, that's corresponding on the x-axis, up to here, the function is increasing. So you'd say f is increasing on the interval from negative infinity to a, and then again from b to infinity it's increasing again as you go from left to right. So you put a little union symbol, b comma infinity. And notice we use parentheses everywhere and we don't use brackets, because at the points a and b, we're not including them, the function is turning there. And here in between, as you go from left to right, you're going downhill. So if you drew a stick guy, he's going downhill, whereas over here, he's climbing uphill. That's the best of my drawing skills. Anyway, f is decreasing, we would say, on the interval from here to here, a to b. Okay, this part, where it's decreasing. So it's always the x-axis intervals that we are looking for. Also notice that the function has a maximum there, a relative max, or I'm abbreviating, it's a relative maximum. Because relatively speaking, in that neighborhood, it's the high point. It isn't the highest point, it's not the absolute max, because this function keeps growing. There are points higher, but in this region where it turns, it's a relatively or locally a maximum point. Similarly at b, you have a relative minimum. Okay, so if I say REL, relative min, I'm talking about a relative minimum point, which in the local area, in this neighborhood, that's the low point. So think of this as a peak, and that is a valley, the low point. We'll finish off the first half of lectures for this section with a definition. And this definition has everything to do with these turning points where important things do happen. And this point where the turning happens is called a critical point. A critical point, or a critical number, is an x value, okay, where the first derivative f prime is 0, or it could be undefined. If you have a graph that looks like this, right here, this point is a vertical tangent line, and there f prime does not exist. Okay, so x is equal to c is a critical point of a function f of x if x equals c is in the domain. It needs to first of all make sense that it works for the function. It can't be somewhere outside the domain. Okay, so x equals c is in the domain of f of x, and either f prime of c equals 0, or f prime of c does not exist. Take the equals off there. So either the first derivative is undefined at c, but the function is defined at c, and that could happen, or the derivative could be 0. So we're going to put all this together with a quick example, and so for this I'm going to direct you to print off the worksheet 4.1a. So the first question here is one where the graph is given to you, and you need to determine the intervals where f is increasing, constant, or decreasing. And remember, we always go from left to right when we describe, and when we say intervals, we're talking about the x-axis intervals. So left to right, what is the function doing at first? So going from left to right, it is decreasing, and then it is constant, and then increasing. So how do we describe this part? Well, this goes on forever. So go from left to right, this part on the x-axis correspondingly, f is decreasing on the interval from, the number here is negative infinity, comma, negative 1. Then between negative 1 and 1, f is constant. So f is constant on the interval from negative 1 to 1. And finally, f is increasing on the interval from 1 to infinity. So that's this portion, going on forever. So now the next example we have has some other parts. We have a function given to an algebraic form, and we need to answer some questions determining how to find the critical point. So to do that, if you go back to your notes, you're looking at the critical point is where the first derivative is 0 and first derivative does not exist. And after we do that, we're going to look at this statement here. If f prime is positive, like here it is, that's the critical point. So you pick a sample point here. If f prime is positive, the function is increasing. If f prime is negative, the function is decreasing. Alright, so let's do that here. To find the critical point, you need to take f prime, find the derivative, and in this case it's easy, the 2 comes down, so you have 8x plus 7. And then we need to set this to equal 0. We need to see where the derivative is 0. So if you solve this equation, subtract 7, divide by 8, this is the critical point. To answer the second part, where we need to find the intervals where the function is increasing and decreasing, what we do is draw a number line. We place the critical point. This is the only spot where the function is going to be turning. If there were other points, we would have gotten them by taking the derivative, but we didn't, so this is it. So if this is 0 and this is negative 1, negative 7/8 is somewhere here. So I'm going to split my number line right there. I'm going to pick some sample points on this side of negative 7/8 and then some other sample points on this side of 7/8, negative 7/8. And what we're going to do is, let's say we pick negative 2 and let's say we pick 1. These get plugged into f prime. F prime is over here. If I plug in negative 2 for x, that's 8 times negative 2 plus 7, which is a negative number. It's negative 16 plus 7, it's negative 9. I don't really care about the 9 part of it. All I need to know is what the sign is. Because if f prime is negative, let's go back in our notes. If f prime is negative, then f is decreasing. So f is decreasing. Now let's take 1 and plug it into the derivative. F prime at 1 is 8 times 1 plus 7, which is a positive value. It's 15. But again, 15 doesn't matter as much as what the sign is. If the function's derivative is positive, the function is increasing. So the final result would be, you would say your answering the question, f is decreasing, going from left to right, on the interval from negative infinity to negative 7/8, and f is increasing on the interval from negative 7/8 to infinity. So I hope that makes sense. Let's see what else is left on this worksheet here. We have a couple more examples. We're going to repeat what we did before. To find the critical points, remember the critical point is where f prime of x is 0 or f prime of x does not exist. Okay, so let's find the derivative. F prime of x, the 2/3 comes down, then x is raised to 2/3 minus 1, which is negative 1/3. So that's going to go here. In the last chapter, I did not force you to simplify, but now those days are gone. We need to clean it up before we can go further. If you have a negative exponent, goes down below, so it's x to the 1/3 down here. Now to answer the question, critical points happen when the derivative is 0. So here's a logic I want you to think about. We have a fraction here all cleaned up. How is a fraction equal to 0? What should you have in a fraction? If you have a over b, a fraction, if it is 0, how is that possible? So if you think about it hard enough, you might think that, it might come to you that it must be only if the top is 0. So for f prime of x to be 0, it means that the numerator is 0, which is just a constant 2, which is a false statement. So this part of the critical point does not happen. What about this part? Well, where is f prime of x undefined? It is undefined if the denominator is 0, and that does happen if x is 0. So if you put 0 in here, that's a cube root of 0 is 0, and 0 times 3 is 0. So it's undefined if x is 0. Is this in the domain of the original function? Meaning, can you find f of 0? If you plug in this 0 for x, is that a value that works? The answer is, this is 0 minus 2. Yes, it's in the domain. So x is equal to 0 is your critical point. So that was a little bit trickier than the first example. Anyway, we're done with the hard part. To find the intervals where the function is increasing and decreasing, what we did in the last example is we drew a number line. Just to keep our work organized, we put in our critical point. We sampled points from either side. Now we didn't have to take negative 2. We could have taken negative 1 or negative 3. On this side, we could have taken 0 or 2. No matter what you pick, you'll get the same results. Okay? So with that being said, here's our number line. There's 0. Split it. Let's say we pick negative 1 on this side and 1 on the other. Plug it into f prime. Here's f prime. F prime at negative 1 is 2 divided by 3 times negative 1 to the 1/3. Now the cube root of negative 1 is negative. It's a negative 1. So it's 2/3 times a negative 1, you get negative 2/3. If f prime is negative, what is f doing? Again, check the notes. If f prime is negative, function is decreasing, so f is going down. For this side, if I plug in 1, f prime at 1, that's 2 divided by 3 times 1 to the 1/3, which you can clearly see is a positive result. Now you could have plugged in 2 or 3 or anything in here for x, it would be positive. Whereas on this side, no matter what you plug in, you get a negative result. In other words, f here is increasing. To write your answer in the end, you need to put it in interval notation, going from left to right. F is decreasing on this interval from negative infinity to 0, and f is increasing on the interval from, it's going up from 0 to infinity. Now on a graphing calculator, if you were to type this in, go to y1, type in x caret 2/3. If you have an old calculator, you'll need parentheses. Caret is for exponent, minus 2. You should get a graph that looks kind of like this. I don't have my calculator on me right now, but this is the shape you should have. And that should match what we have here, where f prime is decreasing first and then increasing. And notice how it's a sharp turn. That's something we learned in chapter 2. The sharp turn is due to the first derivative being undefined at 0. Alright, very last example here is a rational function. So right away you know that this has a domain issue. What can x not be equal to? If you were to find the domain here, you can easily tell that x can't be 3, or you'll be dividing by 0. So let's move on to part A, critical points. To find f prime, you can either use the quotient rule or bring this up and use chain rule. If I use the quotient rule, derivative of top 0 times the bottom, minus keep the top, derivative of the bottom is 1, all over bottom squared. So this is 0 times anything, so it's still 0, 0, and that's minus 1. So it's just negative 1 over x minus 3 quantity squared. We'll do the same logic as in the previous problem. To find the critical point, we see where f prime is 0. For a fraction to be 0, it means that the top is 0, which never happens. So no critical point from there. Again, following our example from before, f prime of x is undefined if the bottom is 0, and that happens if x is 3. But 3 is not in the function's domain, original functions. So, not in domain of f of x, which means we can't use it. In other words, there are no critical points. All this work for nothing, but we still can go on and figure out the intervals where the function is increasing and decreasing. As in the previous two problems, we draw a number line, but in the previous problem we took the critical point and split it. But here we don't have a critical point, but at 3 the function is undefined, so I'm going to put an open circle right there. Okay, open circle because x can't be 3. Put a little arrow and say x can't be 3. And we can do what we did before, pick sample points on either side of this point. So let's say we pick 0 and 4. Plug them in into the derivative, f prime at 0. If you go here, plug in 0, it's negative 1 over 0 minus 3 quantity squared. Anything quantity squared is positive, and you have a negative on the top. So it's going to be negative 1 over 9, which is negative. If the derivative is negative, f is going to be decreasing, so it's going downhill. If you plug in 4, f prime at 4, here's f prime, negative 1 over 4 minus 3 is 1 squared. We still have a negative on top, so it's a negative 1. So at this point, something to notice is that this derivative always will be negative, because unless it's undefined, because this is quantity squared, it will always be positive unless x is 3, and there's a minus 1 on top. So anyway, back here this is still decreasing. The function is decreasing. To finish up and write our answer as we did before, go from left to right. It's not all real numbers as you might mistakenly think, because there's actually a hole there. So the way you would write it is you would say f is decreasing on the interval from, start from left to right, negative infinity to 3. union, notice the parentheses, we're not including the 3, union 3 comma infinity. Alright, that brings us to the end of the first half of 4.1. The next video will have the rest of 4.1 along with 4.2.